The incircle omega of the acute angle triangle ABC is tangent to its side BC at a point K. Let AD be an altitude of triangle ABC, and let M be the midpoint of the segment AD. If N is the common point of the circle omega on the line KM distinct from K, prove that the incircle omega and the circumcircle of triangle BCN are tangent to each other at the point N. So we draw the perpendicular bisector of BC and find its intersection with NK, which we will label P. Because if NBPC is cyclic, then P will be the midpoint of arc BC, and by the shooting lemma, N will be the internal tangent of omega and the circumcircle of BNC. We know by the midpoint on altitude theorem that NK can be extended to meet the AX center of triangle ABC. And in order to prove that NBPC is cyclic, we look at point P. We can find that P is in fact the midpoint of IAK by looking at BXKC and showing that they're equal. So in order to prove that NBPC is cyclic, we must prove that NK times KP equals EK But however, because we know that P is the midpoint of KIA, then we find that NK P. Now, in order to prove this, we construct the midpoint F of NK. And because our goal is to prove that FBIAC is cyclic, we must look at the circumcircle of BCIA. We know that ABC is the orthic triangle of IAIBIC, which means that I, which is the orthocenter of IAIBIC, CIAB is cyclic. However, we also know that because NK is a chord and F is the midpoint of the chord, then IFK must be a right angle, and therefore so will IFIA. However, since IAIA is the diameter of the circle BCIA and IFIA is 90 degrees, we know that F lies on the circle, thus proving that FBIAC is a cyclic quadrilateral, and therefore so is NBPC. Thus, finishing with the shooting lemma, the circumcircle of BCN is tangent to omega at N.